Okay, so today we're looking at double angle identities, and double angle identities really are just an extension of the sum and difference identities. So here again are the formulas. Make sure that you have these on your formula sheet. Make sure you have these in front of you and you apply them when you see them. Part of this is you need to be familiar with these identities so you can recognize when you are running across one of these identities. And one of the things I want you to just make sure that you recognize is, first of all, these are just related to, I'll go over the first one here. This one, sine 2 alpha, is 2 sine 1 alpha times cos 1 alpha. So that double angle is generated from those single angle identities. So for cos 2 alpha, it's going to be cos squared minus sine squared. Okay. And again, I'm going to prove these in a bit, and they're just based on double angle, the sum and difference angle identities. But really, to go from this identity to these two, we're just going to add in the Pythagorean identity. And we're just going to say, for example, the sine alpha is equal to 1 minus cosine squared alpha. And if we replace this sine alpha here, okay, we end up with minus 1, well, there's our minus 1, minus cosine squared, so we have 2 cosine squared, so we get our 2 cosine squared alpha there. And the same thing can be applied with this identity here. If we replace the cosine squared with a equivalent Pythagorean identity, so we have cosine squared alpha, like that. We replace that cosine with 1 minus sine squared, well, we get, there's our 1, we have minus 1 squared alpha minus 2 squared alpha. Okay, so there it is. For the tangent ones, the first identity is just taking the double angle sine over the double angle cos, so it's basically sine over cos, which is tan. The other one is, I'm not too sure if these are on your formula sheet, but if they aren't, you can put them on. But this one is just a rearrangement of these ones. These two, in fact, if you divide this top by cos squared and the bottom by cos squared, we can generate this one here. So there's a few for tan there. Okay, so let's prove this identity, okay, for the sine 2 alpha. We're going to prove it just using the sum identity for sine. Okay, so the sum identity sine for looks like this. Sine of alpha plus alpha, which is 2 alpha, is going to be sine alpha cosine of the other angle alpha plus sine of alpha cosine of alpha. Well, if I put those together, those are 2 sine alpha cos alphas. So there it is. We've just generated the double angle identity for sine by using the sum identity. The same thing can be done with cosine. Okay, so I'm just going to plug it in. So for cosine, it's going to be cos alpha. And for if it's plus here, it's going to be minus here. It's going to be sine cos minus sine. So sine alpha. So cosine times cos is cos squares minus sine squared alpha. Okay, so there it is. There's our double angle identity for cos. So fairly easy to generate. These are just based on the sum identity. Okay, for tan, we can just do tan alpha. We can do as sine of alpha plus alpha over cosine of alpha plus alpha, and we can generate those identities this way. So we end up with sine alpha cos alpha plus sine alpha, cos alpha cosine alpha, and that's going to be over cos alpha. Oops, sorry, that's going to be sine cos. It's going to be cos minus sine. Okay, and then again we generate that double angle for sine to sine alpha cos alpha over cos squared minus sine squared. And then if we want, you can just divide that top and bottom by cos to generate the other identity. Okay, so we can verify these by just graphing them. So if I want to compare these, okay, I would graph y equals cos 2 alpha, for example, and I would graph that against y equals cos squared alpha minus sine squared alpha. And we can compare these. These should graph on top of each other. Well, we know this one here is just a horizontal compression of cosine from 1 to pi. So it becomes, instead of period of 2 pi, it becomes period of pi. When we graph this, we should expect this to map just right on top of that graph. Okay, so I'm going to show that on Desmos.